Oh, I'm on now? Oh, I need to repeat what I said. Well, welcome everybody. Can you hear me in Idle Falls? Raise your hand. Hello? Raise your hand if you can hear. Oh, that's in 16. All right. Well, they're waiting. Okay. All right. The Elmo overhead. The camera. Okay. Just to quickly review, how do we get a grade out of this, last part of this class? Well, basically, it starts with showing up. Second, thinking. Third, yeah, you got to do a little bit. Okay, so this is the second of 3 weeks. Next week is closed week, and we will have class during closed week. Okay, so there is a weekly summary. A lot of you have done this. It's due, end of day on Friday of this week. Basically, a one-page, blurb of what went on in the 2 sessions of that week. Okay. In addition to that, and that's due on Friday, and then there's a PowerPoint presentation pretending that you're presenting to a group. You're going to put together some information on a topic of your choice having to do with electrical engineering. 10 to 15 slides, and that'll be due Friday the 11th. Okay? And then another part is a question. I want everybody to submit a question. I don't guarantee all questions will be answered, but I guarantee that I'll know whether you submitted a question or not. And please put that on a separate email, and I will attempt to address some of those questions as we go on. Okay? Any questions? All right. Okay, back to the computer screen. One question that was asked, well, what's the earning potential of engineers? And so I was just up here, and this is on the government site. I said, well, let's compare it to actors. Anybody seen any movies lately? I guess actors, like engineers, there's a few stars that make a whole lot of money, and then everybody else makes okay. So anyhow, just looking at actors here, 2006, 163, 182. I mean, those probably aren't the star actors, all right? All right, just as a comparison, let's go back and look at this. And you guys can do this on your own time too. But you look at professional engineers. And where'd it go? Yes, earnings. Okay. So we just look at the median. Well, let's look at the high, the highest. Over here on this side, aerospace engineering, computer hardware engineers, and petroleum engineers, nuclear engineers. Okay, those are garnering the higher paid positions at this point in time. Generally, those are in areas of the economy where there's lots of opportunity to make money. Petroleum engineers, of course, and in the business producing, fuel and gasoline for the transportation industry, and there's a lot of growth around the world on alternative energy. A lot of money being spent in that direction. So, a lot of mechanical, a lot of electrical work that'll be going on in that area over the next few decades, I'm sure. So I'm sure that this will probably change a little bit. So, you're on a good course, right? Hope you feel better in 4 years. Just think, just 4 short years and away you go. Okay. All right, so that was one question. Another question had to do with what is a solid state drive? Kind of a computer-oriented question. Basically, a regular hard drive that we're most familiar with in our computers is an electrical mechanical device. Has a spinning platter inside that has magnetic material on it, and the information is stored by writing and reading magnetically information on the hard drive. And so, and that's the bulk of hard drives are like that. Now, a USB drive, like a thumb drive, is kind of like a solid state drive. But they do also, because it's all solid state, there's no mechanical part that's spinning or moving inside. But they do also manufacture what they call solid state drives that basically fit the same form factor, emulate what the actual hard drive does, and so you can simply replace a regular hard drive with a solid state hard drive, and it uses microelectronics solid state memory in order to store the information rather than electromechanical device. Okay, another question. What do double E's have to do with nanotechnology? If I spell that right, technology. Okay, nanotechnology is, of course, looking at things on a very small scale, down to the nanometer, if you will, 10 to the minus 9, in that order. Being looked at in the area of medicine, biosystems, in the double E realm, it's kind of like a cousin to microelectronics production, and when we build a microprocessor, the features on a microprocessor are down to the 1.3 micron level, which is not, quite at the, the nanometer level, but they also use microprocessor, or you should say the process to create, the microelectronics, what they call MEMS, which are mechanical electrical devices that are on a very tiny, small scale. And so that's kind of the bridge between nanotechnology and what double E's are doing in the microelectronics process arena. Another question had to do with what is power electronics? Oh, I'm sorry. Could you do the overhead for me, Elmo? You guys should have spoke up, so you're right, and it's like talking into the wind, doesn't do any good. They need to have a button here on the front that I could do this myself. I'm sitting here writing, and you guys aren't seeing anything. Okay. So, power electronics. Power electronics encompasses a fairly, it's kind of like a renaissance, if you will, ever since the personal computer came out, for that matter. There is a need to have smaller, lighter weight power supplies. And so, historically, they have what are called linear supplies, but most of the activity is in the area of switcher supplies that are usually also under some kind of microprocessor control and use switching technology in order to generate different voltages and currents. Even on a motherboard on a personal computer, for example, you have a main power supply going into your computer, but in order to reduce the power dissipation on the CPU itself, it needs power that's, say, less than traditional 5 volts, and so there'll be power devices on a motherboard to take a 5 volts DC and convert that to 1.8 or 2.3 or whatever the needs are of the microprocessor itself. Also in the realm of alternative energy sources, there's just a whole host of needs of power electronics, everything starting with the photovoltaic, or the windmill generator, to a controller that takes the energy from these sources and then packages it in a form that's usable for other devices that we have. I mean, you can't take your refrigerator right here and directly plug it into photovoltaic and have it do something. You have to collect the energy, you have to process it with power electronics, and then you feed it back through your regular panel on your home in order to supply all your regular loads that you're accustomed to. Okay? So, and of course, another big area of power electronics has to do with the automotive industry, with the advent of electric vehicles or hybrid vehicles. They're just full of opportunities of engineers that can do that, as well as usually when you're talking about power electronics, you're also talking about portable, and you have to get into different battery technologies. What kind of battery, the chemistry of the battery. Batteries, you can't just simply hook up a supply to them and charge them. They have to kind of be babysat, or they have an early life failure and that sort of thing. So it takes electronics in order to make all that happen. So a lot of upcoming opportunity in power electronics. Okay, so those are some of the questions that came through last week. So look forward to that some more. All right. Would you, everybody's had the roll. Pass the roll back down this way. And somebody on the back row, would you run it across the hallway to the other section if you wouldn't mind? Okay. Today I'm going to introduce you to a, some fun things that electrical engineers get to think about. But it's amazing. I mean, you're really fortunate that you can go to school and have computers to help you. And it wasn't all that long ago that people went to school and they actually didn't have computers to help them. And maybe you had to learn more, or maybe it took longer. I don't know. It's a little different. But I'm going to introduce to you, we have the computer, a tool that electrical engineers use all the time. And we call it SPICE, which is some acronym that means something. I'm not sure what it means, but it basically is a circuit emulation. Now, I know you guys aren't, electrical engineers or, circuits, but I'm sure that you've all driven cars. You probably replaced batteries in cars and flashlights. Anybody put up Christmas lights and half the lights are dead? And you try to debug those silly things. Drives me nuts. So anyhow, circuit simulation is a bread and butter tool that we use. And there's places where you can get this tool. It costs you absolutely nothing. It's amazing what's available. And so a company called Linear Technology that makes parts to sell in the marketplace. They also provide a design tool called LT Spice. And so if you're interested and you go to their site, you can download this tool and play with your heart content. Okay, so basically a circuit simulator helps us, aids us in the analysis of a circuit. So I'm going to go through a couple examples. So first off, the easiest kind of circuits to look at, and these are basic circuits, are what we call DC, or a direct current circuit. And so, a resistor divider, which basically means resistors in series, is a very common application to look at a circuit. So we can put 3 resistors out here, and I need to get a go V voltage, A voltage source. And a voltage source is represented by a circle with a plus and a minus representing a positive, negative terminal. And we need to get out a ground symbol. So I put a ground down here. And then after we have these components out here, we get to wire them up. So here's my wire. Boy, I wanted to do something weird down here. All right. For some reason, wanted to rotate my ground. I guess I got tired. All right. Now, if you do need to edit, this particular tool has a pair of scissors right here. You can come along and trim your wires so they look nice. Okay. So let's assign resistance to these resistors. Lower right click here, and we'll say it's 100 ohms. Another right click, 100 ohms. Another 100 ohms. And then on the voltage source, we're going to give it a voltage of, say, 12 volts. Okay? So this is what we call a series circuit, meaning that the elements are in series. And because they are in series, we think of the current flowing out of the positive terminal of the source, flows in this direction, down through first this resistor, the second resistor, and the third resistor, and then back to the source. One thing about electrical circuits is that there's always a return path in this case, okay? And so, let's see, what else do I need to put? I already got that. If I here under, I have a simulation command window here, and there's different types of simulations, and I'm not going to, of course, cover all of them, but they're fairly broad and they're get used quite often. But in our case, we're basically looking at what we call a DC, and when we select this, all we do is we select it and say, hey, we just want what we call the DC solution of this circuit. And so, I don't know where this guy came from. And then we hit the runner up here, and that's our say to run. And so we say, okay, run this for us. And then it runs it, and then gives us this result right here in this pop-up screen. Okay, so up here it gives the voltages for each of the nodes, and we define a node, anything that interconnects two elements. So you have a node, node doesn't have anything to do with the length of the wire. It just says, well, between this element and that element, that's what we call a node. And then also between these two resistors, this is the node here. Now, when you build a circuit like this, the computer will give you node voltages, and that's what this V parentheses N 001 is. So it's assigning numbers so that each node is unique and that sort of thing. Now, in some of your other engineering disciplines, if you're if you're doing analysis like designing trusses or doing finite element analysis, I mean, you have nodes and things like that associated, so it's kind of similar, and I'm sure that you'll use some of those programs as well. So in this case, it gives us the node voltages. Notice node 1, which is the positive end of our source, V1, that is 12 volts. Good thing. That's what we said. We said that source is 12 volts, and it reported back, yeah, it's 12 volts. And if you look at the current, because these elements are in series, the same current flows through everything. And so the current through the 3 resistors is given in amperes, which is 0.04. You can see that they're all equal. And then it's also the same current that flows through the source. And the reason it shows negative through the source basically has a terminology, if you will, that current flowing out of the device is expressed as a negative quantity. Current that flows in a device is expressed as a positive. But the magnitude is the same because it's a series circuit. Okay? Now, being that these 3 resistors, and if you're familiar with Ohm's law, these 3 resistors, we call this circuit a voltage divider. Why? Because the 3 resistors, they spread across the full voltage of 12 volts, being equal in value, they're going to divide that 12 volts into 3 parts that are equal. And that's what we see. We have this point being 12, this point being 8, and this point down here being 4. So in other words, there's 4 volts across each resistor, being that they're equal. Okay? You probably already knew that. Could have done this by hand. Right. Okay. Well, let's just change our circuit slightly. I guess I gotta get out my scissors here. Well, I just start. Easier to start over than just move it around. Let's just use another configuration. We'll give it the same value, 100 ohms. And we'll wire all these guys up. Yeah. Well, it wants me to go all the way back, I guess. Sometimes dealing with the computers, sometimes challenge, I guess. So this configuration obviously is, well, maybe it's not obvious, but it's in, they're in parallel. Okay, I think we got them. Same voltage, but in parallel. Same operation as before, so we should be able to just hit run at this point in time. And it goes through and it calculates our result here. Okay, so again we see, I mean, how many nodes do we have? Well, we have ground, which is 0, and then we have this node up here, which is the same voltage coming out of the supply, and so that's 12 volts. So in this case, we have less nodes. We have 3 elements in parallel, which means that the voltage across them is going to be the same, which is 12 volts. And since the resistance is the same, then the current flowing through those resistors is also equal. The total current is the sum of the three, which is 0.36, which again flows out of the positive down through. By the way, it's kind of by convention that we take current flow in a positive sense. Current flow actually can be handled by different polarity of charges. In a wire, that which helps you have current flow or is available of electrons. And so electrons are moving. Well, electrons are negative charges. So in a certain sense, the current is flowing in the opposite direction. So it's kind of odd in a way, but it just kind of means that it didn't really matter. But we generally think of current as positive flow, current flowing out, which is really the opposite of the direction the electrons are actually moving. Okay, but in semiconductor materials, you can have charges that are positive, and so then you do have positive flow. Plus, if you're into batteries or electrochemical solutions, you have both positive ions and or negative ions, and so your current flow can either be by positive charges or negative charges. But anyhow, just to kind of mention that by convention, we take current as being positive current, if you will, which may or may not be the actual direction of what the current is flowing. Okay. All right. Well, now we have other kind of sources that we like to use. This is a voltage source, and so I'm going to change it, and we're going to use another favorite source we use all the time, which is a current source. And I'm going to rotate this so it's pointing in the direction I like to see it point, and put it in there. And we'll give it a value of, say, 10 amperes. A lot of times, because our sources that naturally exist, like a battery, they tend to generate voltage. And so we probably spend most of our time thinking about sources as being voltage sources. But there are some instances where we can model a system more effectively or operates more like what we call a current source. And let me maybe explain it this way. A voltage source, we say an ideal voltage source will give us a constant voltage independent or regardless of the current that flows through it. And that's an ideal voltage source. And an ideal current source will give us a current irrespective of the voltage that's across it. And so you'll always just produce that much. And so the sources that we use in our simulation here generally are all ideal, and then if the system is not ideal, then we add the things to make it model the actual system. So anyhow, this is an ideal current source, and I say, okay, give me 10 amperes of current, and that's what he does. Okay? So, given I have 10 amperes of current flowing through 3 equal resistors, how much current do you think would be flowing through each resistor? These resistors are acting as what we call a current divider. Each one will take a share relative to its magnitude to the other ones that are in parallel. Since they're all equal, they'll take an equal share. And there's 3, then it should be like divided by 3. So we'll see if the computer agrees with that. An analysis basically the same as before. And so basically here's our current source right here. We said it was 10, and so it gives us 10 amperes. And then through each of the parallel resistors, we get 3.33, which is a third. And the voltage is simply, this current being multiplied by the total impedance of this. The equivalent impedance of three resistors in parallel, they add reciprocally. So it'd be 33.33 ohms. Multiply that by 10, and that gives us this node voltage of 333.33 ohms at the node right here. Okay? More than you ever wanted to know, huh? All right. Well, let's do another type of a circuit. And bring out a new schematic here. And again, we'll get a voltage source. And a resistor. We'll rotate this. And then we'll get a capacitor. Grounding node. Now, I assume all of you have had a little bit of physics, maybe not, where you've studied capacitance a little bit. If not, maybe this will just serve to spur your interest. Okay, now here I'm going to have to follow some of my own notes here a little bit. Here we'll give this a 1 ohm resistance. Capacitance, there's kind of like three major elements that we use over and over again. Is, of course, resistors is a big thing. A capacitor is a device that doesn't really conduct electricity directly. In other words, if I were to do a DC solution on this, there'd be no current flow because capacitor basically is two conductors that are in close proximity to each other with a dielectric in between. Dielectric is really an insulator. And so there's no current that actually flows through as in a DC sense. But it will store a charge and stores energy. And so if it's a transient kind of a condition, which means that the voltage or the current is changing as a function of time, then that charge will have an influence and there will be a transient voltage or current that actually flows through the capacitor. So, and the value of the capacitor is in farads, and we give it 100 microfarads, and we put a U there to indicate micro. And on this guy, we really don't give him a DC value. We have to come up here and change our, what we're going to do is we're going to do a transient simulation rather than a DC steady state simulation. So we need to give it a stop time, which is in seconds. So this is going to run for 10 milliseconds. And let's see what else. Go to advanced here. And so I'm going to select a different source. Instead of a constant DC source, I'm going to select a what we call a pulse. And basically it's going to be a series of pulses, but because my simulation isn't going to go that long. We're only going to just see one pulse. And so I give a starting value of 1. It starts at 0, goes up to 1. And there's all kinds of different parameters we can give this, and I'm not going to explain it all, of course. Later on, if you do take a EE course, you'll be very fond of this and be quite familiar. Well, maybe not fond, but certainly familiar. And basically, because we have a resistor and a capacitor circuit, and we give it a pulse of energy, the capacitor just doesn't instantaneously change the voltage on it. The voltage will change on the capacitor as current flows in it, the charge will build up, but that is going to be moderated by the resistor. So we have a RC cooperative system going on here. Okay? And so let's just see if this will work. We hit run. And I'm going to close this guy. So in this particular case, instead of just printing out values, it gave me a plot screen automatically. And then when I come down here on my circuit, you can see how my little cursor changed to a little probe. And so I can say, oh, well, show me the voltage here. So I always like to see what my source is doing to make sure things are what I expect. And in this case, it is. Basically, what I wanted to do is create a pulse where I start at 0, I go up to 1 volt, and then I stay constant, and then I come directly down back to 0, and then constant at 0 for the rest of the time. Okay? And we use these kind of signals all the time in electrical circuits when we want to verify different parameters and things like that. We have function generators equipment to do this on the bench. So this is our source, okay, the green line. Then we come along here and we're going to probe and see now what the capacitor is doing, and which is the blue. I'm sure you guys in the back can really see that, right? I'm going to zoom in and look at that, make this larger. Okay. Well, probably. Anybody see that blue? Blue on black's not the best choice, I guess. But okay. So anyhow, what the simulation tool is allowing us to do is and this has application in all phases of engineering or whatnot. You know, if you're a bridge, you're a civil engineer. I mean, here you have a span of bridge and you have a heavy truck that goes over it, where you got a bump, you know, and then all of a sudden a load is delivered onto the bridge. I mean, there's some movement. You know, and that's, you know, the transient, maybe some vibration, maybe a little bit of quiver or oscillation. And so, in this case, what we see when this pulse immediately goes up, well, the voltage across a capacitor does not immediately change. But it goes up in this curve right here, which is an exponential curve. And the equation here, just give it to you, is 1 minus e to the minus t over tau, where tau is the time constant, equal to the resistance times the capacitance. Could you show the Elmo? I guess I need to add my... And I mean, these exponential equations, regardless of which engineering discipline you go into, they just show up time and time and time again, one way or another. And basically this is, you know, for the case where you have in this case it's a capacitor that's being charged up to a final value. And so based upon the choices of the R and the C we have, R being 1 ohm and C being 100 microfarads, this time constant here is 100 microseconds. Now, our time constants are generally pretty quick, pretty short compared to other kinds of systems. Particularly if you're in nuclear engineering, you're looking at decay constants. Some elements are very, very, very long. Most of ours tend to be pretty quick. So, and so where is this point? Or I should say, here you have this exponential curve. How do we relate that to a time constant? Well, when one time constant has gone by, in other words, this is time here, where is 1 tau? One time constant or 1 tau. So when tau is equal to t, then this equation is 1 minus e to the minus 1. And of course, all of you know what e to the minus 1 is. Everybody knows what e is, right? But e to the minus 1 ends up being 0.367. And so this whole value right here ends up being, well, we express it like 63.2%. So, in other words, what we look at is over here. Can you show the computer again? Go up here and get a cursor. So if I come out here, I'm looking on my horizontal. When I hit 100 microseconds, that's one time constant. Some more, come on. Right there. Okay. So my final value is at 1. And we use 1 a lot just because, it's easy to do some of this math. It's easy to know where 63% of 1 is. It's 0.63, right? So if you look down here in this window for my cursor at the horizontal setting of 1 microsecond, I'm at 0.634 volts or 634 millivolts, or as I just on the other equation show, that's 63% of the way to the final value. And so, that's what one time constant is in this transient response. Okay? Now the other thing you can do here is go back. Let me just add one other thing to the circuit. Let's add a inductor. He's kind of big, but we'll try to make him work. Big in size, not necessarily big in value. But we're going to put the inductor in series with the capacitor. Okay? Now, oh, come on. Wire here, will you? Now, inductance is another element that we use all the time. And its units in henries, we're going to say it's 1 microhenry. But we find inductance everywhere where you have a current that flows. It's just one of those things, just kind of like you have capacitance everywhere because you have insulation in your system. And so you have inductance because you have current flow. If you have a wire, current flowing in the wire, there's some inductance associated with that. Sometimes we take advantage of that by wrapping the wire around an iron core and turn it to a transformer, a solenoid, or something like that. But sometimes we don't want the inductance. Why is that? Well, if you have kind of like a switching circuit like this, and you have some inductance in it, we look at the output here. The input's the same, but if we look at the output here across the capacitor, it changes the behavior here. Let's see, what do I want to do? I think I want to make this a little larger here. My resistance is small. Well, go back. Basically, what you could end up with is yeah, okay. This will work. So let's see, where are we here? This is the output right here. Get all my screens confused. Okay. Now notice this shape right here, and notice the voltage. Well, I started out on my source down here. I said, okay, go up to 1 volt. All right. But if you look at this, which is looking at the output on the capacitor now with the inductance in, I have a voltage here of 1.4 volts. And so basically, with the interaction of inductance and capacitance, the system can will oscillate at times and give you voltage levels, if you will, that are larger than what you started with. And so this is typical of a lot of systems that oscillate. If you get into a resonance kind of a situation, you could have forces set up that are much larger than the original force that started the oscillation in the first place. So, could you show me the computer? I'm sorry, we're stuck here on the overhead. Again, you guys are out there and say, "What are you talking about?" It was on the computer? Oh, I'm looking at these screens. I get confused, I guess. Back to the computer. Sorry. There. So, oftentimes people use electrical analog and SPICE as an analysis tool to understand what's happening in a mechanical system or a nuclear system as well. And so this has application across other engineering disciplines. Okay. Well, I don't see any hands, so I assume there's no questions. Make sure you got your name on the roll if you're here. If you're not here, don't put your name down. And we'll see you on Wednesday.